So we ended the last lecture talking a little bit about limits of vector-valued functions, and that sort of leads nicely into the concept of the derivative of a vector-valued function. So the derivative of a vector-valued function, say x of t, y of t, c of t, I'm guessing that you could probably make a good guess. To take the derivative, you just want to take the derivative. So we'll just put r vector prime t. You just take the derivative of each component function. And that follows immediately from the limit and kind of the properties, the addition and scalar multiplication properties of vectors. Okay, so that's the derivative. But probably more important is kind of what the derivative actually represents. So notice also the derivative is a vector-valued function. So the vector-valued function so what is it going to do? It's going to output vectors, just like r of t, that are, so think back to Calc 1, derivative is tangent, is the slope of the tangent line, so the output vectors are going to be tangent to the curve. Given by our original r of t. And we can also define something that plays a role. So if we want to know the direction, for instance, of the tangent, we can define the unit tangent vector so it'll be t of t, and it's just r prime of t divided by the length. So it's just the unit vector in the direction of r prime. And what you should think about the unit tangent vector in the back of your mind is it's the direction that the particle is moving at any given time. Just like the tangent, or this r prime of t, the derivative, is pointing in the direction that the particle is moving, but it just has its magnitude, its speed, whereas the unit tangent vector is just giving the direction. So let's give a little visual of what's going on here. So again, let's just for simplicity say we're in the plane. And here we have some curve oriented this way. So this is like the motion of a particle. And so of course we have our position vector. So our vector valued function that's giving us our position, or in other words, it's parameterizing the curve or the motion of this particle. So the derivative is going to point this way. It's going to be tangent to the curve, and it really is just the velocity vector. So this is a particle, we're just moving along here, and this is just the direction, and the magnitude is the speed that it's going. And so down here It'll point this way and this way. So yeah, so hopefully that gives a visualization of what's going on. And then the unit tangent vector, of course, is just the direction, right? So it's just the unit vector in the same direction as the velocity. All right, so we have another notion to discuss. A curve. Of course, I'll just start using curves and vector valued functions kind of synonymously, even though maybe there's a little distinctions. But a curve, R of t, is said to be smooth if, and so let's be a little careful. I should say it's smooth at t equals a if the derivative exists there. So that's similar for Calc 1, but there's something else. So if the derivative exists there and it's also not equal to 0. So a point where the derivative is 0 or the velocity is 0 for a curve is a point where the curve is not smooth. And the way we can think about this is if I have this curve, so I have a velocity, so I'm moving, and let's say I stop. I stop right here. So here my velocity is 0. Then I'm free to go any direction I want. I don't have a direction vector here telling me where to go. So at some later time, I can just shoot off this way. And you see that I kind of have a cusp going on in my function here. So that's the way to think about it. If I'm driving my car with a non-zero velocity, I'm moving smoothly. But if I stop, I can then instantaneously start moving in some other direction. So that's a point where my curve is not smooth. So because these vector valued functions are just inherently vectors, we can actually operate them with our familiar vector operations. So dot product, cross product, we can add them. And so it's nice to review the properties and how they behave with differentiation. So first of all, let's say I take two vectors, vector valued functions, and add them together. Take the derivative. Well, hopefully by now you're not too surprised that this will behave somewhat like we expect. It's just the sum of the derivative of the two vector valued functions. I mean, this isn't quite as obvious as just for regular functions of one variable from Calc 1. You still have to think about it, but it's not too hard. And then also, we can multiply a scalar valued function, so just a regular function of one variable, so these are just going to be scalars at values of t, times a vector valued function, and take the derivative. And here's where it gets a little interesting. We actually have to do something sort of like the product rule. So this is like f prime of t times r without taking the derivative, and then plus f of t times the derivative of r. So very much like the product rule. And in fact, all the different ways we have to multiply functions are going to have a very similar product rule. So if I have two vector valued functions and I'm taking their dot product, that's going to give me a scalar valued function. If I take the derivative, well, it really is just going to be, I take the derivative of 1, but now multiplication here is not like scalar multiplication, it's actually a dot product, so it's the derivative of r dot s of t plus r of t dot the derivative of s of t. Okay, and then actually the same thing is true for the cross product as well. So if I have the cross product of two vector value functions, this itself is going to be a vector value function, and the derivative of that vector value function is going to be, well, it's going to follow the product rule as well. So I take the derivative of r cross with s, and then add r crossed with the derivative of s. And then the last thing we can think about is, what if I have a composition of functions? So let's say I have a vector valued function that I'm actually, instead of just plugging in values of t, I'm plugging in some sort of function composed. So some function of t, and so it's going to be r composed with f. And f here is just another scalar value function. Well, this is going to be very similar to the chain rule. So I get this scalar value derivative times the derivative of r still evaluated at f of t. So these properties, I'm not saying you should memorize them, I'm just saying you should know that they exist, things like them, because they just pop up from time to time. And the good news is there's nothing too surprising here. Things sort of behave the way you want. And I guess I should say that I'm assuming the derivative always exists. Of course, if you know f here is not differentiable, this doesn't make sense. But assuming that these functions are differentiable, then this all makes sense. Okay, so the last thing we want to talk about is integrals. So we talked about derivatives. Now let's talk about integrals. So the definite integral of some vector valued function r of t, I think we need to assume that all the component functions are continuous or something like that, but let's not sweat too much about those details. Everything we'll be working with will surely be at least piecewise continuous. Okay, so the definite integral of this function, say from t equals a to b, well, take a wild guess. It's going to end up being a vector. And what are the components? Well, the components of the vector are going to be the definite integrals of the component functions. So you may be asking, what does this even represent? Well, this is just areas under the curves in different directions, and then the vector is just giving us kind of an orientation. And this actually will be very useful in applications when we want to relate, say, position, velocity, and acceleration. And similarly, the indefinite integral so the same r of t, so recall that when we have a indefinite integral of one variable, we get this plus c, this integration constant, but we're going to get one in each component. So we're actually going to be adding an integration vector, so an arbitrary vector, to our antiderivative of r of t. So it's going to be antiderivative of the x component function, antiderivative of the y component function, antiderivative of the z component function, and then plus some arbitrary constant vector that has an x, y, and z component. That's basically just picking up the plus c here, and plus c here, but they could all be different. So I think that's all we need to know about the calculus of vector value functions. All right, so let's get to work. So first of all, we just want to take the derivative and actually evaluate it at a. So first we'll just take r prime of t, and what do? Well, we just take the derivative of each component. So 2t, 3t squared, and then we'll just plug in this case a is equal to 1, so we'll just plug in 1, and we get the vector 2, 3. So that's the velocity or tangent vector at the point we're interested in. And just for good measure, we'll just plug that in, so the position vector there is 1, 1. We'll need that later. And then 2, we just want to find the unit tangent vector, t of t. So what do we have? We have the unit tangent vector is just the derivative vector divided by the length of the derivative vector, which is going to be, so 2t, and then we'll divide each component by the length. That's just going to be the square root of 4t squared plus 9t to the fourth. And then here we have 3t squared over the length, which is square root of 4t squared plus 9t to the fourth. Okay, so there's the unit tangent vector. And then finally, we want to sketch these two vectors. So the curve we can just kind of trace it out a little bit. So when t is 0, we're at 0, 0. So it's just going to kind of come out like this. In fact, we can actually figure out exactly what the curve is just by, okay, so we have y is equal to t cubed and x is equal to t squared, so therefore y is equal to x to the 3/2. Okay, so it looks something like that. And our position vector, so if here's 1, 1, here's r prime of 1 right here. So here's r of 1, the position at 1. When t is 1, we're pointing to the point 1, 1. And then the tangent is 2, 3. So it's going to be a little bit steeper. It's steeper going this way. So here's r prime of 1 going up that way. And it's supposed to be tangent to the curve. It doesn't look like, well, there it is. Okay, so here we have another vector function, and we're going to take the derivative and evaluate at pi over 4. So we'll start there. So first, find r prime of t, which is equal to negative sine t, cosine t. Okay, and then I evaluate at pi over 4, I'll have, this is going to be minus root 2 over 2 and root 2 over 2. And then, again, just for good measure, the position vector at pi over 4 is just root 2 over 2, root 2 over 2. Right, so the unit tangent vector is just going to be the derivative divided by the length, but something nice happens here. So what's the length of the derivative vector? Well, it's just sine squared equals cosine squared, so that's just 1. So the unit tangent vector is actually just equal to the tangent vector. Okay, and now let's sketch our function. We know that, well, this is just living on the unit circle. So we have our curve. It's a little poorly drawn. It's supposed to be a circle. Okay, and then our position vector, pi over 4, is going to go here to root 2 over 2. So here's our pi over 4. And then our derivative vector is going backwards to the left and up. It's going to be tangent to the curve going that way, so there's r prime pi over 4, that vector right there. Okay, so we want to find the derivative and then the equation of the tangent line at the specified point. And then think about, well, are there any points where the curve is not smooth? So first things first, let's take the derivative. That's just going to be 3t squared. We got to use the product rule here, but it actually simplifies really neat. It just becomes t plus 1 squared e to the t, and then 3 cosine of t. Right, so we want the equation of the tangent line. So we're going to use the vector form of the tangent line. So recall that for the equation of a line, we need a point on the line at, in this case, 0, and then we need an equation in the direction of the line. Well, that's just going to be our derivative vector. So actually, the equation of the line is just going to be at t equals 0 is going to be r of 0 plus r prime of 0 t. So this is a point on the line at t equals 0, and then this is a vector in the direction of the line. So this is going to be r of 0 will be 0, it's going to be 1 and then 0 plus r prime 0, again 1, 3. Okay, and there's the equation of the line, tangent to the curve at that point. And then are there any points for which the curve is not smooth? Well, we're looking for t-values for which the derivative is either undefined or 0, and we see that there are no points. So actually r of t will be smooth for all t. Alright, so we'll start by taking the derivative again. S prime of t will be, this will be some chain rule, so 2 sine t cosine t, and then we'll have a negative here because when you take the derivative of cosine we'll get negative sine, but other than that it'll be the same thing. Oop, not sine t, sine t. Sine t cosine t. Okay, so t is between 0 and pi, and then we want the equation of the line tangent to the curve at pi over 4. So the tangent line again has this nice form. We just need a point on the line. That's going to be s of pi over 4. And then vector in the direction of the line, that's just the derivative of pi over 4. And this is very much acting like the slope. Okay, so what happens when we plug in pi over 4? Well, sine of pi over 4 is 1 over root 2, so squared is 1/2, so this is going to be 1/2. And actually cosine is the same thing. And then here, well, sine and cosine of pi over 4 are both 1 over root 2, so again, this is just going to be 1/2 times 2, so that's just 1, and this is going to be the same thing, but negative 1. And that'll be our equation of the tangent line. And so where is this function not smooth? Well, we want the derivative to be 0, and that's actually going to happen when either sine is 0 or cosine is 0, but between 0 and pi. So t equals 0, t equals pi over 2, and then t equals pi. S will not be smooth. And that corresponds to points where it stops and then turns around. Okay, so we're supposing that there's just some arbitrary curve and it lies on the surface of the sphere, x squared plus y squared plus z squared equals 1. And we want to show that in that case, the position and the velocity are always orthogonal. Okay, so the key observation here is that if I look at the length of a vector, which, recall, so if I square it, this is just the same thing as the vector dotted with itself. What is this? This is the length of the vector squared, but it lies on the sphere of radius 1, so the distance from the origin is always going to be just 1. Now what I want to do is differentiate both sides of this equality. And I'm going to use my rule for differentiating the dot product of two vectors. This is going to be, well, take the derivative of the first guy, dot the second, and now they just happen to be the same thing, plus the first dotted with the derivative of the second, and then the derivative of the right-hand side is 0. So in other words, Recall that the dot product is commutative, so these are really the same term. 2 times the dot product, r prime and r, is 0, but 2 is not 0, so the only way that the left-hand side is 0 is if this is 0 right here. Well, what does that mean? That means that, well, the dot product of two vectors is 0. It means they're orthogonal. But this is true for any t. So this tells us that r prime of t, r of t are orthogonal for all t. Alright, so we want to evaluate this indefinite integral. But as we've seen, to evaluate the indefinite integral, we just want to take the indefinite integral of each of the components. Here, here, and here. So our components, our x component, will be just the indefinite integral of 1 plus t squared dt. But that's just going to be t plus t cubed over 3 plus a constant. I'm going to call that constant cx, because it's the x component, and it's going to be the x component of the constant vector. Okay, and then y will have integral of t to the minus t dt. Well, how do I take the antiderivative here? Well, if you really want to get down to it, I believe this is like a integration by parts problem, but you can integrate by parts, or you can just sort of think about it. And I believe the derivative of this function will give me exactly this. I mean, if you don't believe, just integrate by parts, or just use a calculator at this point. I mean, we're through Calc 2, so we don't really need to sweat about that too much. But I do have another constant that I'll call cy, and then the z component will be the antiderivative pi t, which is going to be negative cosine pi t over pi, and then plus another constant, which we'll call cz. So the indefinite integral of our function, vector value function, is just going to be, each component will be the antiderivative that we found, and then we have this plus c vector, which has components cx, cy, and cz, which can be arbitrary. Because if I take the derivative of this, when I take the derivative of a constant vector, it'll give me 0. And so I'll just get exactly r of t.